Welcome all of you to this module. We considered the least squares formulation for the linear regression problem, and I mentioned to you that we can have alternative metrics. One such metric would be the maximum likelihood estimation of the parameters given the data. So, let us see how we can estimate the parameters for the linear regression model. We consider data points xi, yi, and I can go from 1 to n. These are our observations. We consider the model yi is f of xi plus epsilon I, where f is the true relationship between xi and yi, and epsilon I, we assume this is normal distribution with 0 mean and variance sigma square. So, all the observation noise samples epsilon I obey this distribution. We assume that xi and yi are IIDs, they are IID random variables, that means they are independent and identically distributed random variables. Our linear regression model implies that the estimate of y, which is yi hat, is alpha naught plus alpha 1 xi. So, given the data point xi, my estimate of yi is given by yi hat according to this linear relationship. Let us use the vector formulation that will help us to simplify the mathematics a little bit. Now, let this vector alpha given by alpha underscore be interpreted as a 2 by 1 column vector comprising of alpha naught and alpha 1. We have x interpreted as a column vector comprising of 1 and xi. Therefore, I can write yi hat, which is estimate of y, as an inner product between these two vectors alpha transpose and x, right. It is yi hat is basically alpha transpose x. This is a compact form of representing this estimate. So, yi hat is a scalar and I can realize the scalar using the dot product of two vectors. Yeah, a small detail before we end this slide. I mean, we have these pairs, right, xi, yi, and those pairs are IIDs, that is I take x1 y1, I take x2 y2, I take x3 y3, pairwise they are IIDs, right, they are independent and identically distributed, and that is the distinguishing thing, and you need to write this within the braces. Now, let us formulate the likelihood function in terms of the parameter, right. Our parameter here is alpha that we need to estimate. Assuming they are IID, I can take the product I going from 1 to n, the probability of this observation yi given xi. Now, I simplify this. Now, what is yi given xi? It is basically the noise, right. It is basically the noise epsilon I, and we simplify this in this form, and we know the distribution, which is Gaussian. So, therefore, I have 1 over root of 2 pi sigma square, and this term is basically my epsilon I, yi minus yi hat is my noise. Now, I can use the vector formulation for my estimate of yi, and I plug that in. This gives me alpha transposed xi, and you have to note that all of these are essentially scalar quantities, right. Now, I have this in this product form which looks quite messy, and I can simplify this likelihood function by taking the logarithm of this function. Okay, taking the logs on both sides of the likelihood function, we get this quantity here. So, the L stands for, the small l stands for the log likelihood, and if you do a little bit of algebra, you will simplify this to this quantity here. Observe that minus 1/2 summation I equals 1 to n log of 2 pi sigma square is a constant term, and we can ignore this when we have to maximize the log likelihood function, and this term comprises of this vector alpha, which is the unknown which we will have to estimate given our yi and the vector xi. Okay. Now, what we do is we set dl alpha upon d alpha transpose to be equal to 0, and then we solve for this. So, maximizing this log likelihood function is tantamount to minimizing just this quantity summation I equals 1 to n yi minus alpha transpose xi square, right. This is an important observation. So, maximize the log likelihood function, we have to minimize the term j which is given by this quantity, because there was a negative sign sticking there. So, we got rid of it and we have this in terms of the positive quadratic cost. Still, this is not easy for us to simplify, because we want to invoke matrix calculus. Now, you interpret this error ei to be yi minus alpha transpose xi. This is a scalar quantity, right. This is a scalar quantity. We set up some vectors that will help us. Now, we stack the error observations for I going from 1 to small n. So, I stack all these errors and I interpret this as an n by 1 vector, right. This is an n by 1 vector, and y comprises of observations y1 through yn, and this is an n by 1 vector which is a column vector, and I formulate a matrix which is capital X by stacking all these vectors x1 through xn over observations 1 through n, right. And this x1 vector, if you recall, is this 2 by 1 vector as per our definition here that we defined very early. So, going by this, we formulate a matrix equation. Now, the cost j is basically E transpose E, which can be written as y minus this matrix x times alpha transposed times y minus x times alpha, right. The matrix X is an n by 2 matrix consistent with our notations, and the vector y is an n by 1 vector, and you can just check the sanity, right. This is an n by 2 and this is a 2 by 1. So, this gives me an n by 1 and y is n by 1. So, everything is sane in our formulation. Now, let us proceed with our simplifications. This cost j is basically y minus matrix x times vector alpha, the whole transposed times y minus x times alpha, right. There is a vector alpha, alpha is a vector. So, we were missing this underscore. So, j equals, now I simplify this quantity here, this is y transposed y, because A minus B whole transpose is A transpose minus B transpose. So, I use this this algebra. So, I get y transposed y minus y transposed x times alpha, and alpha there is a bar here indicating it is a vector. Similarly, I have alpha now I take alpha transpose x transposed y plus alpha transposed x transpose x times alpha. So, there is a bar sticking under alpha, right, indicating it is a vector. Now, we have to look at all the terms where alpha appears, and if you are careful, we ignore this y transpose y, we ignore. The middle two terms can be simplified as minus 2 times x times alpha transposed times y, and the last term is a quadratic in alpha. So, we write it as alpha transpose x times alpha, right. We treat it like this. Now, we take the partial of this cost with respect to alpha transpose, and we set this equal to 0. So, if you take the derivative, we do matrix calculus. So, you can look at my video lectures on matrix algebra in the mathematical methods and techniques for signal processing course. So, there is a video lecture on matrix calculus. So, using the rules of matrix calculus, you can take the derivative of these quantities with respect to a vector, because alpha is a vector, we take the derivative with respect to the vector. So, you do a little bit of algebra, we get this quantity here, which is minus 2 times the matrix x transposed y plus 2 times the matrix x transposed the matrix x times this vector alpha equal to 0. Now, this is a matrix equation, it is not like a scalar equation. So, what we have is x transpose x times alpha is x transposed y. Now, it is straightforward to compute alpha as x transposed x inverse times x transpose y, right. You pre-multiply by x transpose x inverse on both sides and you get this result. But what is important to observe is that this inverse of x transpose x should exist, right. This is the important observation. And why did we land up with such an equation like this? Because we had n observations and we just had 2 variables to estimate, which is alpha naught and alpha 1, because of which we had more observations and less variables in our model, and we landed up with our observation matrix which was rectangular, and because of which if we have to have an inverse, we have to have a square matrix, we land up with a pseudo inverse form like this, right. Now, you may question if the inverse x transpose x of x transpose x, the inverse of x transpose x, if it exists. If it exists, there is no problem, we can solve for alpha uniquely. If we cannot solve for it, then we will have to eliminate the variable, or we have to look at some sort of regularization for this matrix equation under certain conditions to solve for alpha. Okay. So, this basically simplifies our derivation for estimating the model parameters in the linear regression model using the maximum likelihood estimate. So, we have learned 2 techniques, one using the quadratic optimization using residual square sum, the other is using the maximum likelihood estimate. So, depending upon what is convenient to you, you can use the techniques appropriately. Now, having discussed this idea with observation noise for the simple regression case, let us analyze the regression problem over multiple variables, see how this becomes slightly more involved and complicated, and what we can do to simplify these things. Okay. Let us consider the multiple variable linear regression problem or multivariable linear regression problem. Suppose we have more than one variable, suppose we have more than one variable, say p predictors. These are my variables. For example, if you think about the agriculture example involving the crop yield problem, we have the pH content of the soil, the moisture, pest control, etc., etc. These are all the variables that I have, right. Now you set up the residual square sum as summation I equals 1 to n yi minus y hat square, right. For every observation that I have, which is yi, I have a corresponding estimate. This is true observation, this is the model, which is yi hat. I formulate using the least squares criterion again. Now we do the simplification, which is basically summation I equals 1 to n, I just replace yi hat with this quantity, right. Since there is a negative sign sticking with respect to all the coefficients alpha naught hat, alpha 1 hat, etc. Now the goal of the problem would be to minimize the residual square sum with respect to the parameters alpha naught hat, alpha 1 hat, so on till alpha p hat, right. I have to minimize this quantity with respect to these parameters, and if I optimize that, I will get alpha naught star hat, so on till alpha p star hat. Okay. Now you may wonder why I did the analytical form for the single variable case. If you did the calculus here taking the partial derivatives with respect to all these quantities, it is going to be a very tricky problem and also cumbersome, right. We do not want to proceed in this direction because sometimes the number of parameters in practical examples can be 20 variables, 25 variables, and it is impossible to set all the derivatives with respect to these 25 variables and then solve this problem, right. So what we do is follow the popular gradient descent approach towards solving this problem. How do we proceed? The residual square sum is a function of this alpha hat, where alpha hat is a vector that comprises of all the parameters alpha naught through alpha p. So I stack them as a column vector and I formulate alpha hat. Similarly, I formulate a vector x which is 1, I should put an index here which is xi, which is going to be 1 xi1 dot dot till xip. So since I have p variables and for the term alpha naught I do not have anything there, so it is going to be 1. So therefore I have this as 1, right. This is just rewriting this equation that I have earlier in this form in the form of a matrix, right. So I just express it in terms of an inner product of alpha hat with xi, and then I put this in this form. Now the gradient descent approach tells us that my solution to alpha hat at time t. So, this is the update step. Normally one would use small n for discrete quantities and this variable t for continuous, but since I am using an n already here in terms of the number of data points, I am bringing this variable t here. Okay. So, this is my update step and this is discrete, and alpha hat at time t is alpha hat at time t minus 1 minus some eta, this is a learning parameter or learning rate, times the gradient of the cost with respect to the alpha hat at time t minus 1. So, it is a negative gradient. So, therefore, there is a negative sign sticking here. So, this is the update rule, and using this update rule we can solve for alpha hat in one shot. So, we can get the entire vector in one shot. If you are not comfortable with this vector form and doing this gradient with respect to the vector, you can collapse it to the scalar form and then solve for each of these variables in scalar form. Okay. Now, one of the questions that we have to ask, particularly from a practical standpoint of view, what should we do to make the gradient descent work? Now, I have this equation, does it work well in practice? If you think about practical data points, the scaling will be quite different over different attributes. For example, I may have the age between 0 to 120 years for human beings. Say if I look at the population, if each individual has x number of children, right, it may be 0 to 7, 10, we do not know what is that number, right. So, we can have various attributes, and these attributes may not be on the same scale, for which we will have to normalize. So, there are two steps that are very important for the gradient descent algorithm to work. One is scale normalization, the other is mean normalization. So, we will discuss both of these quantities. So, first is the feature scaling, right. So, let us take this example for say two variables. The first variable x1 is the age variable 0 to 120 years, x2 is the number of children, say 0 to 7 children. So, I formulate x1 tilde is x1 upon 120, just normalizing with the maximum number of years here in that population, and x2 tilde is x2 upon 7 normalizing over the variable x2, right. So, I can formulate like this. So, now this is within 0 to 1. In this case, you know, the children and the age is it cannot be negative, it makes no sense, but there can be certain attributes that can be negative. For example, if it is a bank balance, then it could be negative. If you are owing something to the bank, it can be negative, it can be having negative values. So, everything is within a -1 to +1 range. Then we can consider mean normalization. For this, we need to replace each xi with xi minus mu I, that is, we remove the bias out, and normally we can do the mean normalization post the feature scaling, and if you are savvy you will observe that this does not apply for the x naught I equals 1 case, because that is there is no mean for that variable there, it is 1, right. For all the others x1 I, x2 I, so on till x p I, we have to do the mean normalization appropriately. So, this should now work. So, if you formulate things carefully, that is, you do the feature scaling and do the mean normalization, and then take your transform data and do the gradient descent, it should work, and you have to choose an appropriate learning rate for that algorithm. Okay. Now, after having studied this, we have a few important questions that we need to ask. First question: do all the variables help in predicting the quantitative response? For example, think about this advertising problem. I am advertising over the newspaper, over the radio, over the television, over the social media. Are all the predictors equally contributing to my response? Possibly not. There could be a few dependencies, right, or there could be certain quantities that are statistically insignificant. So, this is very important to assess. How well does the model fit? That is the second question to ask, right, because we have to compute the RSS and then we have to figure out if we can simplify things further, right. This is an important thing. Then, given the predictor values, what response value do we predict? At the end of the day, if you have to do any forecast, it is difficult because it will have implications. For example, if it is a policy or decision making, maybe at the governmental level we need some statistical model to predict something, and based on this decisions are taken. So, therefore, it is very important to have sound models, and then we have a notion of accuracy of this model, that is what is a good fit and what are the right statistical indicators. So, these are very important parameters, and I think though the model which is the linear regression model is kind of pretty old, and I would say one of the basic bare bones in statistical modeling, it is a very important model to study because it has quite a lot of implications. So, we will stop here and then we will look at other variations of this regression model, including interaction effects.